Good afternoon, everyone. Welcome to the first undergraduate seminal series for the final quarter of this year. Speaker today is again Lourie Bosman, third year physics student. He's going to talk about who invited pi.
All right. Thanks everyone for coming. Pi needs no introduction. It's such a famous number, such a ubiquitous number, and in a lot of cases that shouldn't come as a surprise. Considering it is the circle constant, you would think anywhere that you see a circle, pi might show up. And since circles are such fundamental objects, so they show up pretty much everywhere, it's no surprise that pi shows up pretty much everywhere. Today we're going to look at three problems where at first glance you wouldn't expect pi to show up at all. Where's the circle? But hopefully by the end of today I can convince you that these three problems do in fact have a fundamental connection to circles and to pi. All right, without further ado, let's start with the first problem. The famous Basel problem. Yeah, this is one of my favorite problems in math just because of how simple it is and how confounding the result is. And to make it even clearer how strange this result is, I'm going to pose it in the way that it was originally posed back in the 1700s, I think. I forgot the date, but so we're going to start with a simple problem that looks something like this. Consider the series of reciprocals of sums. And my question is, does this series converge? And if so, to what? Solving this is not tricky. All we need to do is we need to consider these denominators, in particular the sum, let's do this with k. The sum of the integers, as you might know, gives you this result. These numbers are also called the triangular numbers, if you're not familiar. So our sum over here, our series, simply becomes the sum of our 2 over n times n plus 1. But then, with a little bit of partial fraction magic, we can simplify this. I'm taking the 2 out for simplicity. It becomes 1 over n minus 1 over n plus 1. And you can check me on this. If you add these together, you get n plus 1 minus n over n times n plus 1, which is what we had originally. But this thing is a telescoping series. If you write it out, you see that the first term is 1 over 1 minus 1 over 2. But then the second term becomes plus 1 over 2 minus 1 over 3, etc., canceling each of these terms except for the first one, which then just leaves us with 2. All right, so that's our first relatively simple result. The second one is a slight variation on this, where we ask, what if we just take the even numbers, the reciprocals of sums of even numbers? Well, hopefully you can see that this is simply a half of the series that we just evaluated, which will just be half of 2, which is 1. So far, so good. Two relatively simple problems with very reasonable results, giving us integers. But now, we're going to ask, what about the odd numbers? Oh. As it turns out, and this is an absolutely crazy result if you see this without any context, is that the sum of reciprocals of sums of odd numbers gives you pi squared over 6. Well, to evaluate this problem, let's simplify a bit first, same way we did with the first problem. If we look at the denominators, we see that these are just the sum of odd numbers, which actually evaluates to the squares. And to see why this holds in general, you can consider just the difference of consecutive squares, which then would become n squared minus n squared plus 2n minus 1. But then these obviously cancel, and you're just left with the odd numbers. So the sum of odd numbers gives you the squares. Now, this problem, this is what you'll usually see in math textbooks or online resources, is that the sum of reciprocals of squares equals pi squared over 6. We are going to take a look at Euler's original proof of the problem, which he discovered a good 100 years after it was originally posed. There is a very good explanation for how to intuit the squareness of pi in this problem by 3Blue and Brown. I'm not going to go into detail about that. If you're curious, I can highly recommend it. But for today, we're just going to look at Euler's solution, which was to take a look at the sine function. In particular, its Taylor expansion, which will then just be x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus etc., etc., etc. Now we're going to divide throughout by x to get what is also known as the sinc function. I'm just going to leave it as sine x over x, which would then give you this series, x to the 4 over 5 factorial minus etc. Okay, so this is one representation of the sinc function as a power series. And we're going to put that away for now. And first look at a different result that Euler, in his original proof, kind of just assumed to be true. He didn't give a formal proof for this. It was only another 100 or so years later that Weierstrass formally proved it as the Weierstrass factorization theorem, saying that specific types of functions, called entire functions, can be represented as products of their zeros. And it's very similar to the way that we do with polynomials. If you take a polynomial and its roots, you can express that polynomial simply as the product of the monomials containing the roots. Now let's consider the sinc function. It looks something like this. It goes through 1 over there. Technically it's an open dot, but some people redefine the function to be defined at 1 at x equal to 0. But then it has zeros at pi, 2 pi, 3 pi, etc. to the left, to the right, and minus pi, minus 2 pi, minus 3 pi to the left. Now, what Euler assumed to be true, and which actually ends up being true, is that you can represent this function simply as a product of these roots, like so. We take the first root, say x equal to pi, and we say 1 minus x over pi. And then the other root, which is on the negative side, would just be 1 plus x over pi. And then we continue the product for 2 pi and minus 2 pi. And so forth. But if you consider these terms, this is just the difference of squares. And so is this. So we can rewrite this as these products. 1 minus x squared over 4 pi squared, etc. Each time taking the squares in these denominators. But now, if you expand this product, something very cool happens. The constant coefficient will just be 1, because in each bracket we have simply 1s there, which sounds about right, because the first constant coefficient in sine x over x is 1. But then if you look at the square coefficient, the quadratic coefficients, every time you multiply these out, the only square coefficients get contributed by multiplying one of these guys by 1. So in our power series representation of sine x over x, you would have the square coefficient, which I'm going to denote by a2, is simply minus, a big minus, 1 over pi squared plus 1 over 4 pi squared plus 1 over 9 pi squared, etc. Now we have two series representations of the same function. And this would only be true if these coefficients are equal. And from here, we can obtain the famous result that's Basel was the town that Euler came from, so it was named after Euler's hometown. Yeah, so we get 1 over 3 factorial, sorry, minus 1 over 3 factorial, our coefficient at the top there, is equal to minus, and I'm going to write this as a sum, 1 over n squared to infinity n equal to 1. And then a little bit of rearranging shows us that the series of reciprocals of squares is simply pi squared over 3 factorial, or pi squared over 6. That's our first result for today. Unfortunately, with this proof, it's not super clear how to intuit the connection to circles, apart from the fact that sine of x is deeply inherently connected to the series of squares, which in of it is a very interesting result in and of itself. For our next problem, I'm going to take a look at something that should be very familiar to some of you, and it is the integral of the Gaussian, which equals the square root of pi. This is also a very strange result if you think about it, because the Gaussian is a function that's typically used to model distributions of populations and so forth. Why is pi here? Where's the circle? There's actually a very nice way of seeing this if we sort of rederive the Gaussian in a way. If we rediscover the reason why the Gaussian is such a fundamental distribution. And we're going to do it like so. Consider the 2D plane, and imagine that you're playing a game of darts with your friends. And each of these darts lands at a random spot on this plane. Let's say we want to model a distribution of dart throws. And we wanted to satisfy two key properties, two very simple properties, actually. I'm going to call our probability distribution F2 of x and y. And our first assumption is that F2 is radially symmetric, which that is, it's a function that only depends on the radius to a point from the origin. And our second assumption is going to be that the x and y coordinates of this distribution are independent. Wait, sorry. No. G1 of x, G2 of y. Also, not a crazy assumption to make. As it turns out, just by these two assumptions, our hands are forced to arrive at a Gaussian type distribution. And I'm going to show that to you right now. The first the first thing to recognize is that these two functions, G1 and G2, that model the x and y parts of our distribution, actually have to be equal. And it's very easy to see if you have a point x, y, and you simply flip it around the y equals x axis, you'll see that these 2 points have the same radius and thus should have the same distribution value, same function value. So it should be, these functions should be independent of whether you're working with x or with y. So we can simply denote it by g of x, g of y. And actually, we can take this even further and imagine that we rotate the axis or rotate one of these points to lie on the x-axis. That function value should still be the same. So this would actually be equal to g of x, g of 0. But these are all equal to the same distribution over here. Oh, sorry, this is g of r, because our x values obviously are there. So we get that f of r is equal to some constant g of 0 times g of r. Now I'm going to do something here. I'm going to assume that g of 0 is 1. The reason I can do that is because we're dealing with a distribution function, a probability distribution function. We're going to have to normalize it anyway down the line, so we might as well just give it some predefined coefficient. And this gives us a very nice, let's erase this. This gives us a very nice relationship. If we take a look at these, we see that f and r and g and r are actually the same. So we see that f of r, and I'm going to expand r out as the square root of x squared plus y squared, is actually just equal to g of x times g of y. This is a, f, f of x and f of y. This is a functional equation, which tend to be quite tricky. But this one is actually surprisingly easy to solve using a little helper function that we're going to define as h of x equal to f of root x. And then rewriting this relationship in terms of h, we obtain h of x squared plus y squared equal to h of x squared times h of y squared. Our function h turns addition inside into multiplication outside. What functions do you know that do this? Of course, it's the exponential. So we have that h of x squared is simply equal to the exponential, which I'm going to write as e to the ax squared. Of course, this would be our base for the exponential, but it is nicer to write it in terms of e for a lot of applications. And then subbing back in, we see that f of x is equal to the very same e to the ax squared. Ax squared. Right. So let me just get this. But if you remember, we're dealing with a probability distribution function, which has to be normalizable. And this is only true if our a is negative, because otherwise this function would simply blow up to infinity at any of the extremes. Right? And this gives us the general form with some degree of freedom a. And right, so I want to look back at the original problem that I posed for you. And as it turns out, this derivation is very useful in solving this integral, because the key fact about this distribution is that it would be, the key fact is that it is radially symmetric. So using that radial symmetry would be very wise. And that's actually what the most famous proof of this result looks like. We're going to do this by multiplying on either, multiplying by e to the minus y squared, because dy because when we simplify this, we obtain a e to the minus x squared e to the minus y squared dx dy. But as we've already discussed, exponentiation turns multiplication into addition. So this simply becomes e to the minus r squared dx dy. And in this case, r squared is simply equal to x squared plus y squared. But then turning this into polar coordinates to abuse the polarness of it all, we simply obtain a 2 pi times integral from 0 to infinity of r e to the minus r squared dr. Now this function has a very simple antiderivative. It is just minus e to the minus r squared, and we're evaluating it from 0 to infinity. If you want to be precise, 2 pi, that's right. Yes, 2 pi. Yeah. Sorry, I'm confused. We have to take the 2 into account, right? So this just becomes, right, yeah, minus pi e to the minus r squared. And evaluating it at the limits, we simply see that it's equal to pi. But then if we loop back to that equation over there, we see that these two integrals are actually the same. So we find that I squared, which is our original Gaussian function, is equal to pi, and hence I is equal to root pi. Great. Hopefully, I've convinced you that there is actually some radial symmetry, some circleness to the Gaussian distribution, which is why we're able to make that that switch to polar coordinates and why it works so nicely. Okay, for the last problem, and this is going to be the main focus of today in a sense. I'm just going to write it out because honestly, it's such a ridiculous result. Clearly, I'm lying to you. This makes no sense. How can you take the factorial of a half, and why is pi there? Well, let's address the first question first. If you think about something like exponentiation, a to the n, in primary school, you would have originally learned that this is defined to be the product of a times itself n times. And by this definition, something like a to the half makes 0 sense. But we can extend this definition, making use of one key property, and it's the fact that exponentiation turns addition into multiplication. And this is very easy to see via the original definition, because if you multiply by a to the m over here, you simply add m iterations of a, and they add together. So making use of this property, you can arrive at a couple of interesting, useful results. Like, for instance, a to the 0 times a to the 1, well, that would just be a to the 0 plus 1, which would be a. But from that, we can see that a to the 0 has to be equal to 1. And very similarly, something like a to the minus n times a to the n, well, that would just be a to the 0, which we just found is 1. So a to the minus n would have to be 1 over a to the n. And then finally, for fractions, I'm going to squeeze it in there, a to the half times a to the half would be a to the 1, but this is just a to the half squared. So a to the half would have to be the square root of a. We've extended a definition that's originally only defined for integers into the reals, and technically into the complex numbers if you want to. So, okay, if we do the same trick with the factorial, and we consider the one key property of factorial, which is to say that n factorial, which is obviously just n times n minus 1 times all the way down times 2 times 1, well, this entire part is just n minus 1 factorial. Using this sort of recursive relationship, and one extra property, which is a bit out of the scope for today, but the fact that we want the extension of the factorial to be logarithmically convex. Don't worry about that. But using these properties, you can arrive at a very nice extension of the factorials into the reals and actually also into the complex numbers. The pi of x is defined in this fashion, and it is an extension of the factorials. But you won't see the pi function a lot. The much more common one is the gamma function, which is sort of a shifted version of the factorial. It's shifted by one unit to the right. And using this extension, you can actually just evaluate a half factorial, which would then be gamma of 3 over 2. But ultimately, you're just going to evaluate an integral. There's not a lot to be said about that. It's not very interesting. So my question is there a better way of understanding why that root pi arrives? And to do that, we're going to be looking at some balls, some n balls to be specific. We define these spherical circular shapes like this. The 2 ball is the 2-dimensional object, which is just a colored in circle, essentially. And the 1 sphere, which is the 1-dimensional boundary, we call S1. And similarly, for in 3 dimensions, the interior of this sphere we call the 3 ball, and its boundary is just the 2 sphere. And then going backwards in 1 dimension, the 1 ball would just be all the points contained within 1r from the origin, and the 0 sphere would be its boundary, just these points over there. And taking one last step back, the 0 ball would just be a single point. Right. We're going to study the volumes and surface areas of these balls and spheres. To do this, I'm going to denote the volume of the n ball by Bn and the surface area of the n sphere by Sn. And I've got a couple of values written down there, which you might already know. Like the 0 ball, we're using the counting measure to define the volume of the 0 ball to just be 1. And similarly, the volume of the surface area of this 0 sphere is just 1, 2. Right. But then the length of our 1 ball, well, that's just 2r. And the surface area of this circle over here is just pi r squared. And so forth and so forth. Hopefully you know those results quite well. But what if you want to generalize this? What if you want to look at a 10 ball, a 10 sphere? Well, to do so, let me get my notes. I will be making use of 3 basic properties. Number 1, we're going to say that the volume of an n ball is proportional to r to the n. I'm not going to prove this. The proof is very technical. It's just a bunch of integration ultimately. But hopefully you can see why this holds true intuitively. It's not too crazy of a result. The thing lives in n dimensions, so its volume is proportional to r to the n. And we can rewrite this in a more useful form as Bn r to the n, where Bn is some coefficient. It's actually the volume of the ball of radius 1, but it's not important. The second property that I'll be giving a little proof of is the fact that the derivative of the n ball, the volume of the n ball, just gives you the surface area of the n minus 1 sphere, which you can see here kind of already holds true. Like if you take the derivative of b1, that just gives you 2. If you take this derivative, it gives you 2 pi r. You can see that it holds true there, at least. But the motivation for why this holds true looks something like this. Consider the 2 ball with radius r. And suppose you increase its radius by some delta r. Well, how does its total volume increase? Well, you can see that this outer area, this little annulus, looks quite a lot like the boundary there, that one sphere. You can approximate this this change in surface area simply as the product of the boundary times the length of the boundary times its thickness, which would be S1 times its thickness delta r. But this is of course just approximate. Physics me wants to write an equal sign. It's just an approximation. But then you can rewrite this. Of course, you can say that delta B2 of r over delta r is equal to S1 of r. And then in the limit, as delta r becomes smaller and smaller, this becomes a derivative. This is not a rigorous proof, but hopefully you can see why this should be true. All right. And this relationship actually holds in general. So we can write, we can say that our derivative of a general n balls volume is simply equal to s minus 1 of r, but we just wrote bn of r as a very nice little product. So let's do that. Let's substitute that in and see that bn r to the n is equal to s minus 1 of r. And then doing this derivative, which is quite easy, you see that, okay, actually, let's write this in a different order. Then we see that the surface area of the n minus 1 sphere is equal to n over r b, bn of r. Because if you take this derivative, the n comes in front, and we just divide by an r, essentially. Right, so we have two relationships. The last relationship that we're going to be making use of, unfortunately, I don't have a nice proof or nice intuition for why it holds, because the pictures that you have to draw become very complicated very quickly. But I'm gonna try my best. So bear with me. And it's the relationship that we say that our surface area of our n sphere is equal to 2 pi r times the n minus 1 volt. And again, you can sort of see that it holds true here. If you multiply b0 by 2 pi r, you get s1. If you multiply 2r by 2 pi r, you get 4 pi r squared. The motivation for why this holds is a little bit complicated, but the idea is if you take your n ball, or your n minus 1 ball in this case, say a single point for b0, and place a one sphere, which is just our boundary of a circle, at each point, this will give you the surface area of our n sphere. Now, in the case of B0, that's very easy to see because obviously you just get a circle. In the case of B1, which is just going to be a line like this, you can essentially place a one sphere at every point along this line. Ugh, this is where the pictures get complicated. But as it turns out, and this is a very elegant result, the surface area that you just created here, this surface area of this ring, is equal to the surface area of a ball that is encapsulated by this cylinder. Again, the proof of this, highly technical, is just mostly just a bunch of integration, but this does hold, you can trust me. Yeah, the intuition for why this holds true, 3 Blue 1 Brown also did a video on this, where he simply projected the outer cylinder onto the sphere and showed that this projection is actually gives you equal surface areas. Right, so we have three relations. I'm going to write them down in a slightly better way. Well, two relations, really. I'm going to write these down like so. Where did I do it? Here we go. So first of all, we see that Sn of r is equal to 2 pi r b n minus 1 of r, but then also Sn of r is equal to, what is it? What did I do? Oh, it's n plus 1 over r times bn of r. Bn plus 1, sorry, bn plus 1 of r. Yeah, so then just combining these two relations to kind of eliminate our Sn's, we see that, where is it? Bn of r is equal to 2 pi r squared over n. Did I do this right? Yeah. Yeah, okay, no, that's right. I'm just shifting the indices. Yes, okay. Times bn minus 2 of r, which gives us a very nice recursive relationship to determine these volumes. And with the conditions that b0 of r is simply 1 and b1 of r is 2r, you can actually go and determine all of your volumes just from this recursive relation. But I want to do better. I want to write everything in a nice closed form. Easy to read, easy to apply. And we're going to do it like so. First of all, notice that, yes. Okay, first of all, I'm just going to rewrite this ever so slightly. Oh my gosh. Sorry, this is chaos. Let me just write, okay. I'm just going to shift the indices once again a little bit in this fashion. So we get bn plus 2 of r equals 2 pi over n plus 2 times r squared bn of r. But then, if you apply this relation to itself again, we see that bn plus 4 of r would just be 2 pi times 2 pi over n plus 2 times n plus 4 r to the 4 bn of r. And actually, inductively, this holds in general. You see that bn plus k of r is equal to 2 pi to the k over 2 over n plus k times, actually let's write this like n plus 2, n plus 4, up until n plus k, times r to the k bn of r. And in this case, k is, of course, an even number. Now we're going to consider this coefficient of the thing. In fact, I'm just going to rewrite it like so. 2 times 2 times 2, because every 2 years is matched to a term in the numerator. Of course, it's inverse, and then we have a bunch of other stuff over here, pi to the k over 2, r to the k, dn of r. We're going to consider that coefficient term there. Specifically, for n equal to 0, we see that, for n equal to 0, that coefficient simply becomes 2 times k, 2 times 4, all the way up to k, all divided by 2 times 2 times 2. And I'm just going to ignore the inverse for now, because we can just add it in later. This becomes k over 2 times k minus 2 over 2 times all the way down to 4 over 2 times 2 over 2, which we can then rewrite as k over 2 times k over 2 minus 1 all the way down to 2 times 1, which is just k over 2 factorial. It's nothing strange here. K is an even number, so this is an integer. Everything checks out. For n equal to 1, we get something slightly different. This becomes 3 times 5 all the way up until k plus 1. And again, there's a 2 to match every term in the numerator, which we can then rewrite as k plus 1 over 2 times k minus 1 over 2 times 5 over 2 times 3 over 2. Again, we can then rewrite this as k over 2 plus a half times k over 2 minus a half times 5 over 2 times 3 over 2. But now, if we assume that, that the factorial is applicable to non-integer values, we see that something like k over 2 plus a half factorial would have to equal k over 2 plus a half times k over 2 minus a half down to 5 over 2 times 3 over 2, and then using our recursive relation, which I erased, but just n factorial equals n times n minus 1 factorial, we see that this thing, it rolls up to there, times a half factorial. So if then we can rewrite our little guy there. Okay, we can rewrite this. I'm going to make a arrow there. This becomes k over 2 plus a half factorial divided by a half factorial. All right, so we've got two relations basically from this. We can see that for n equal to 0, our bk is just simply, and I'm substituting everything back in there, would become pi to the k over 2 divided by k over 2 factorial times r to the k. Did I do? Yeah, right, because our b0 is just equal to 1. And when n equals 1, this becomes twice a half factorial over k over 2 plus a half factorial times our pi to the k over 2. Oh yeah, and then, yeah, okay, r to the k plus 1. This k plus 1 comes from, this k plus 1 and the 2 comes from the fact that b1 equals 2r. But then let's make a little substitution and say that L equal to K. This thing is running up. This becomes A equal to K plus L equal to K plus 1. We can rewrite this relation here. BL equal to essentially yeah, okay. This would be a half factorial times 2 over root 2, root pi, times pi to the L over 2. Ooh, that's ugly. L over 2, all divided by L over 2 factorial r to the L. I've made a bunch of substitutions here, mainly noting that k equals k plus 1 minus 1 equals L minus 1. That's why we have the root pi over there. And then this k over 2 plus a half, that's just k plus 1 over 2, which is L over 2 factorial. But now we can notice something surprising. We have two relations, one for when k is even, and one for when L is odd. But these relations look shockingly similar. We've got the same coefficient over there, and the same little r to the k, r to the L terms over there. The only difference is this coefficient over there. And if we assume, very importantly, there's not a proof that r factorial equals 2, this is just a motivation. If we assume that that relation has to hold for any integer, regardless of its parity, we must have that a half factorial times 2 over root pi equals 1, or rather a half factorial equals root pi over 2. It's my QED. No, that's not QED. It's not good enough for that, unfortunately. Yeah, that's the final result for today. Hopefully, I've somewhat convinced you that factorials actually do have a lot to do with balls and circles and pi in general. Right. Thank you.